Hello, welcome everybody to the Math Girl, and today we are going to talk about truth trees. This is a topic from Discrete Math. Okay, what is a truth tree? So a truth tree is a way to visualize whether a set of premises logically entails a conclusion. So it's like they work on the quote unquote search for a counterexample principle. For example, if you have a conclusion, the truth tree takes the negation of that conclusion, following by the premises, and if every branch closes, which leads to a contradiction, then you can conclude the argument is valid. Okay, so let's do some warm-up here. We're gonna start with the basic implication problem. So first we have the first premise, the second premise, and the conclusion. This argument can also be written in other way. So we have P, if P then Q, not Q. And therefore, start with like the three dots like this, not P. Okay, so first we are going to text everything, both the conclusion and the premises, into a form that just include and or. Okay, so now we have the conditional statement over here. So we're gonna convert them into a statement that concludes only and or. So we have not P or Q. Okay, because we have a rule. That if A then B, this is gonna be logically equivalent to not A or B. You can draw a truth table for that, but since this is like the rule, so I'm not gonna talk about it like in this video. Okay, so now we have this one, and then now we gonna take the negation of our conclusion here. So the negation of not P is not P, right? Which is logically equivalent to P. Okay, so now we have our first line on the branch of the tree. So we're gonna put P up here. Okay, so now let's return to our first premise. This is gonna be our second line. Okay, if you have an or over here, we're gonna branches out the tree. So you branch out like this. Okay, so now we have not P or Q. So not P or Q. Okay, this is first, this is second. Okay, so now let's consider if there is a contradiction in here. You see P and then up to Q. We don't know yet, right? Because there are a different variable. But when you see not P and then up to P, there is a contradiction. Because this branch over here contains both the statement, the conclusion, and the negation of the conclusion. So we're going to say this branch is fail. Therefore, this branch is closed because there is a contradiction in here. Okay, so now we have our second premise. Oh, I'm going to change it to white. Oh, wait. This is going to be our third line. So we're going to put an underline over here, a vertical underline, and then not Q. So we stack it up, right? Okay, let's see if there is a contradiction in here. Okay, not Q up to Q. Okay, there is a contradiction. So now we know that this branch over here, oh, excuse me. This branch over here also has a contradiction. It contains both Q and not Q, which is the negation of it. So we say this branch is also fail. Therefore, it is closed. Okay, if we see all the premises and the negation of the conclusion is failed, which means they are inconsistent. Therefore, we can conclude that our original argument here is valid. All right. Let's move to the second problem, which is the De Morgan dilemma. So in this one, we have, okay, the negation of A and B is our first premise. Our second premise is A, therefore, our conclusion is therefore not B. Okay, so you can find the negation could be written in 3 different ways like this. I prefer the first one here. So I'm gonna write up this one. Okay, so as always, we need to convert everything into and or only statement, right? So we see that is already have an and over here. So now we gonna convert the De Morgan statement here, okay? Okay, by De Morgan's law, we have not A and B is logically equivalent to, not A or not B. Okay, that's our first premise. Now, second of all, we take the negation of the conclusion, which is not B. Okay, so the negation of not B is not B, which is logically equivalent to B, right? So this is our top of the tree, followed by the second is our first premise, and followed by is our second premise here, right? Okay, so now let's draw B. So we have not A and not B. Not A or not B. So we have not A over here or not B. Let's find the contradiction. Okay, there is the contradiction over here. Not B and also B. So this branch here, we have a contradiction which contains both B and a negation of B. So what do we say? It's failed. And therefore it is closed. Okay, and then let's move to this branch over here, which is gonna be followed by our second premise. Okay, our second premise is A. So you stack it up. This branch. Is there a contradiction? There is a contradiction, right? So not A, but A and then up to not A. There is a contradiction. So now, what do we say? It is fail. So it is closed. Okay. Therefore, we have two branches that is closed for the negation of the conclusion. So now we're gonna say this statement here is valid. Right? Let's move to our third problem, the fallacy of affirming the consequent. In this problem, we have our first premise, if P then Q. Second premise, Q, therefore not P. Okay, as always, we are going to convert every statement into and or statement. So let's do our first one. We have P, then if P then Q is logically equivalent to not P or Q. Okay, this is our second, because our first top of the tree, our first line of the tree is the negation of the original argument. So the negation of P, not P, is double negation of P, which is logically equivalent to P. All right, this is our first one, which means the second premise, Q, is going to be our third line of the tree. Now we're gonna have P up here. Okay, second line, not P or Q. Okay, so split it up into two branches, not P or Q. Okay, so now we see a contradiction here. Not P up to P. It is both the conclusion and the negation of the conclusion. So this branch we're gonna say is failed. Therefore, it is closed. Okay, now let's consider the second premise. I'm gonna stack them up. Q. I'm going to label it second and third. Is there any contradiction in this tree branch, in this branch? There is no contradiction. Okay, you'll see over here we have Q up to Q. There is no contradiction. There is no negation. So we're going to say this branch is open. Okay, what does it mean by a branch is open? If a branch stays open, it means there is a consistent interpretation where the premises are true and the conclusion is false. So it is possible that all of our premises are true, but at least to the conclusion is false. Therefore, we're going to say this original argument here is invalid. Right? So whenever you consider a branch of the tree and you find at least, you can have multiple open branches, but if you find at least one open branch, you can jump to the conclusion that the original argument is invalid. Because there is one possible chance that all the premises are true and the conclusion is false. All right.